Hi boys and girls. In the last class we learned about the Karnoff map for three variable Karnoff map. In this video we will see about entry into four variable Karnoff map and corresponding logic simplification. So here we will see some designs, especially the code converters, the binary to gray, the gray to binary, and other mode with a converter with the mode control, etc. So let me start with that presentation. So this page is organized into your learning outcomes, then the design of 4-bit binary to gray code converter, then the 4-bit gray to binary code converter, then binary to gray code converter with the mode control, and summarize with your whatever you learned. So what you will learn in this video, or you will learn you will design a 4-bit binary to gray encoder using Karnoff maps. Then you will design a 4-bit gray to binary encoder using K-maps. Then you will design a 3-bit code converter with a mode control. Like it's a converter, but if the mode is a certain value, say 1, it's a binary to gray code, and if the mode is a 0, it's a gray to binary encoder. So it's a converter with a mode control. Now, when you look about the binary and gray codes, how this conversion comes, it is very interesting. Suppose I have a binary pattern like this, say 0, 1, 1, 0, 1, 1, 0, 1. So the corresponding gray code, if I write, this 0 is mapped as 0. Correspondingly, this is the gray code corresponding to this binary form. What happens is we XOR these values and write this value. So initially it's a 0, so it is written as 0. Then 0 is XORed with 1, so it's a 1. Then this 1 is XORed with 1, and then the gray code is written as 0. Then this 1 is XORed with 0, that gray code is a 1. Then 0 XOR 1 is a 1, 1 XOR 1 is a 0, 1 XOR 0 is a 1, and 0 XOR 1 is a 1. This is how I write a gray code from a binary code. So this is very simple. All you have to do is you have to XOR the successive. You keep the starting bit as such, and keep on XORing the successive bits and the present bit and the previous bit, and so you have a gray code pattern. Now the gray to binary conversion is equally similar, almost similar. Like suppose I have a gray code pattern 0, 1, 0, 1, 1, 0, 1, 1. That's a gray code. Then the corresponding binary, the 0 binary, that's a 0. Then this 0 is XORed with then the next gray value. So it's a 0 XOR 1 is a 1, 1 XOR 0 is a 1, 1 XOR 1 is a 0, 0 XOR 1 is a 1, 1 XOR 0 is a 1, 1 XOR 1 is a 0, 0 XOR 1 is a 1. So this is how I get my binary code back. Okay. So this is how you do the binary to gray conversion and gray to binary conversion. Now I have to design a circuit, some circuits doing this. Now what I have to do is, as usual, I start with a truth table, and then I synthesize a circuit corresponding to that. So let me look at this 4-bit gray to binary code converter. So this is binary bits B3, B2, B1, B0 coming in, and out goes G3, G2, G1, G0. They are the corresponding 4-bit gray codes. So there are 16 possibilities in this. They are outlined like this. Like this is a 0, 0, 0, 0. Then the gray code corresponding to it is 0, 0 XOR 0, 0 XOR 0, 0 is a 0, 0, 1. Like 0, 0, 0, 1, it is a 0, 0, 0, 1. Like if it is 0, 0, 1, 0, it's a 0, 0, then 1, then 1 XOR 0 is a 1. So likewise, you can complete this table. It is something like this. So if I look at the last value, we start the first value is a 1, then 1 XOR 1 is a 0, 1 XOR 1 is a 0, 1 XOR 1 is a 0. So the corresponding code is 1, 0, 0, 0. You can try out this table at leisure, and you can see that is correct. Now I have to realize a circuit that generates, so synthesize a circuits that generates G3, G2, G1 and G0 from B3, B2, B1 and B0. Now if you look in this truth table, you can see that if you by mere observation, you can see that B3 and G3 are the same, because this column is the same as this column. So that means B3 is same as G3. So I have to write truth table for G2, G1 and G0 alone. Now let us write now there are 16 inputs. So it's a 4. It's a there are 16 possibilities. So it's a 4 input Karnoff map. So that looks like this. you can see that this came up, the first one. Let us focus on this figure A. That's for came up for G2. So G2 values are 0, 0, 0, 1, 1, 1, etc. Now let us have a look at this came up. This is let this B0 be the this B0 is my LSB and B3 is my MSB. So I write B3. I partition the truth. I partition the came up in such a manner that here comes a B3, B2 or B1, B0. You can keep the other way also. Only thing is I am keeping this way. Then I enter values like this. This is 0, 0, 0, 0, 0, 0, 1. This is M0, M1, M2. I'm sorry. This is M0, M1. This is M2, M3. Because this is following a both ways it is following a gray code pattern. So this is M0, M1, M2, M3, then M4, M5, M6, M7. Okay, then M8 comes here. M8 is this 1000, not here, it is here 1000. M8, M9, M10, M11, M12, 13, 14, 15. Okay, this is how we do the came up entry. This is how the min times do appear in that. So let me look at those values. These are 0, 0, 0, 0, 0, 0, then 1, 1, 1, 8 ones are there, then 0, 0, 0. Okay, so I enter this way. This is M0, M1, M2, M3. This is 0, 0, 0, 0, 1, 1, 1, 1. Then I have 1, 1, 1, 1. Then remain as 0, 0, 0, 0, 0. Okay. So I get a pattern like this. Suppose I write B3 and B2 here and B2, B1 and B0, then I will be entering this manner like a 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, then 0, 0, 0, 0, 1, 1, 1, 1 that way. Okay. In that case, these two columns would be coming as rows. Okay. It doesn't matter which way you are entering. I'm following this pattern like downward I am entering like 0, 0, 0, 0, M0, M1, M2, M2, M3. M4, M5, M6, M7, M8, M9, M10, M11, M12, M13, M14, M15. Okay. Now you can see that what is the min time corresponding to this these two quads. Now you can see that there are no octets in this. Okay. There are no octets. There are no pairs either. Only quads are there. That is a group of 4. So this I can write as a quad. 1, 1, 1, 1. This is a quad. So if you see that this spans over 4 rows, so everything is changing in these 4 rows. So it is not a function of B1 and B0. It is just a function in B3 and B2 because columns it spans over only one column. So this is the min time corresponding to this quad, that is B3 bar B2. This is 0, 1. So it is a B3 bar B2. Okay, B3 bar B2. So one time corresponding to that it is B3 bar B2. G2 is B3 bar B2. Then the second time is, if you look at, then there is another quad that is happening here. Here you see that it is spanning over 4 rows and everything is changing in that. So it is not a function of B1 and B0. It is a function of B3 and B2 alone. So what is that? It is 1, 0. It is B3 B2 bar. Okay. Okay. So it is B3 bar B2 or B3 bar B2 or B2 bar B3, which is nothing but B3 XOR B2. This is nothing but B3 XOR B2. Okay. Now you know the design for G2. Now we have to look into the design for G1. G1, where is my G1? G1 are these values 0, 0, 1, 1, 1. Okay. Values are 0, 0, 1, 1, 1, 1. Then 0, 0, then 2 zeros, 1, 1, 1, 2 zeros, 1, 1, 1. Okay. So you enter this Carnot map this way. Now you can see that in the schema for G1 you have 2 quads. So one quad appears like this. This is in blue. Okay, this appears in blue. That corresponding time is this spans over 2 columns and 2 rows. Whatever is unchanging here is, if you look here, it is a 0, 0, 0, 1. What does not change is B1. So it is a complement of that B1 bar, because these are zeros. B1 is 0. So B1 bar, here it is a B2. B1 bar B2. So term corresponding to this quad is B1 bar B2. Okay, and what about the this quad appears like this way and this way. Okay, this way and this way. This is another quad. Okay, now here what does not change, or this is B1 is not changing here. B2 bar is not changing, so it is B1 B2 bar. Okay, B1 B2 bar. So when I combine these two terms, it is B1 bar B2 or B2 bar B1, which is B2 XOR B1. Okay, B2 XOR B1. Now G0 is there. Next is G0. G0 is 0 1 1 0 0 1 1 0 0 1 1 0 that way. So it is a repetition of 0 1 1 0. So how do I write? I write a came up like this. It is 0 1 1 0 0 1 1 0 0 1 1 0 0 1 1 0. Okay. Now this results in two quads. This results in two quads. One is B1 bar B0 and this is B1 B0 bar. Okay. This is B1 bar B0 or B0 bar B1, which is B1 XOR B0. This is B1 XOR B0. So the 4-bit binary to gray coder is realized by the following equations. One is G3 is B3 and G2 is B3 XOR B2 and G1 is B2 XOR B1. G0 is B1 XOR B0. If you look at equations from 1A to 1D, you can see that this is how I realize the gray binary to gray encoder. So how does that circuit look like? This is in figure 2. If you look into the circuit, you can see that this is how it is happening. So B3 is the same as G3. Okay, that's a direct connection from B3 to G3, and this G2 is nothing but B3 XOR B2, and G1 is B2 XOR B1, and G0 is B1 XOR B0. Now these are connected to LEDs, and whenever this output goes low, this corresponding LED glows, and you can verify this on the board. Now I will show you a simulation of this using QX. So if I come here, this is a binary to gray thing. This is how I do that. So here you can see that this is my B3, this is my B2, B1, B0, and this is my G3, G2, G1, and G0. So this is this 2 nanosecond, this is a 1 nanosecond, 1 nanosecond, 10 nanosecond, 10 nanosecond, and this is a 20 nanosecond. 20 nanosecond, and this is S3 is a 40 nanosecond, and this 80 nanosecond. If you say it's an 80 nanosecond. So if I run the simulation, these are all XOR gates. If I run the simulation, you can see that the truth table is correct. You can see that it is 0 0 0, it is 0 0 0, 0 0 1 0, it is 0 0 1 1, and if I move it down, you can see that 1 1 1 1, it is 1 0 0 0. You can see that it is performing the binary to gray conversion. Now let me go back to this presentation. Now let us think about a gray to binary converter. I haven't explicitly drawn the truth table. I use the same truth table. Only thing is from this you can see that B3 is the same as G3. I haven't redrawn a new truth table. I use the same truth table. Okay, so how I do here is this B2 is corresponding to this B3 is the same as G3. So B2 is I do a came up like this. It is 0 0 0 0 1 1 1 1 1 1 1 1 0 0 0 0. So this is nothing but G3 G2 complement, G3 complement G2 or G3 G2 complement, which is G3 G2 complement with G3 XOR G2. So B2 is G3 XOR G2. You can draw a separate truth table and you can try this out. And B1 is entered in another truth table. So here it is 0 0 1 1 1 1 0 0 1 1 0 0 0 0 1 1. Okay. Now you can see that you do not have octets or quads. Instead you have pairs. So here there is a pair, here there is a pair, there is a pair here, there is a pair here. So these terms are to be collected. What is the value here for this orange one or the red one? I must say this is G1 and G3 complement, G2 complement. Okay, because this happens in one row and one column and two rows. So corresponding to these columns I have G1 and here I have G3 G2, which is 0 0. So it is G1 G3 bar G2 bar. You can see here I have written these steps here. Okay, you can expand this G1 G3 bar G2 bar, or next term will be my this blue, that will be my G1 bar G3 bar G2, G1 bar G1 bar G1 bar G3 bar G2 is there, G1 bar G3 bar G2 is there. Then corresponding to this orange thing, it is nothing but G1 G3 G2. You can see that the term is here, G1 G3 G2, and then there is a last one in green color here. This is nothing but G1 bar G3 G2 bar, G1 bar G3 G2 bar. Okay, so I can combine some of these terms, like if I take this G1 out of these two, it will be G3 G2 or G3 bar G2 bar, which is G2 XNOR G3, and this is G1 bar is taken, so it is G3 G2 bar or G3 bar G2, which is G2 XOR G3. So you can see that is G1 XNOR G2, G2 XNOR G3, or G1 bar and G2 XOR G3. Now this two input XOR and XNOR are complement. This of the form some A B bar or A bar B, which is nothing but A XOR B, which is, so this becomes G1 exclusive or G2 exclusive or G3. Now if you look at the min times corresponding to this, you have no option, because there are neither pairs nor quads or octets, only singles are there. All you have to do is you have to manipulate algebraically. For G0 you have to B0 you have to manipulate algebraically, and you have to get this equation. This you can do at home. You can see that it is G0. If I combine these terms together, take all min times and add them together or over them together, I get B0 is G0 XOR G1 XOR G2 XOR G3. Now that circuit looks like this. This circuit, this is G3 is the same as B3. B2 is nothing but G3 XOR G2. Now that thing is XORed with G1 to get B1, and the whole XOR, that is XORed with G0 to get my B0, because I told you XOR is an associative function, so I can cascade them like this. So this B2 is nothing but G3 XOR G2, and B1 is G3 XOR G2 XOR G1, and this is G3 XOR G2 XOR G1 XOR G0. So these are connected to the outputs, and you can verify these outputs by connecting on the board. I will show you a simulation in Qux. I will close the present once. I will open a greater binary. You can see that the circuit is realization of the circuit I showed in the presentation. Now I can run a simulation. Now you can see that this is doing the right kind of conversion. This is a 0 0 0 0, it's a 0 0 0 0 0 1 0, it becomes a 0 0 0 1 because it is 1. Then it is a 0 0 1 0, it becomes a 0 0 1 1. And last one, if you say 1 1 1 1, it's a 1 0 1 0. Okay, if I look at 1 0 0, it's a 1 1 1 1. Okay, so it is doing the conversion correctly. Now let me go back to my presentation. Now we can have the converter that converts both ways, like binary to gray and gray to binary converter with some mode control. Suppose in this this truth table, you can say when it is a 0, it is doing like when the mode I have 3 inputs. It's a 3 bit converter. Actually it's a 3-bit code converter with the mode control. So the mode control becomes the last bit, so that's why it is written that way. But it's a 3-bit mode 3-bit code converter. So if the mode bit m is a 1, it does a gray to binary, and if it is the mode bit is a 0, it does a binary to gray conversion. Okay, if the mode bit is a 0, it does a, if these inputs are coming, it's a 0 0 0. If the mode is a 0, it performs a binary to gray conversion. If the mode is a 1, binary to gray, it's the same. If it is a 0 0 1, if it is a 0, it's a 0 0 1. If it is a 0 0 1 1, mode 1, it's a binary, it's a gray to binary, that's a 0 0 1. Okay, then it's a 0 1 0, this is a 0 1 0 0, this mode bit is a 0, so it is a 0 1 1. This is doing a binary to gray conversion. If it is a 1, it does a gray to binary conversion with 0 1 1. Okay, so if you closely follow this truth table, you can see that whenever the mode bit 0 is coming, it is doing a binary to gray conversion, and if it is a mode is a 1, it is doing a gray to binary conversion. Now what I have is the outputs x, y, z this way. Okay, these are my converted output, these are my inputs. Now you can see that this you can see that this x and a are the same. Okay, this x column and a column are the same, so I don't have to do any separate column for that. So all I have to do is x is a, connect a to x, and there it is. Now I have to draw 2 k-maps for y and z. So if I look into this k-map, this is 0 0 0 0 1 1 1 that way. Only the last thing is a 0. If you here you can see that for y it is 0 0 0 0 is m. This is AB, A is MSB, and M is LSB. Okay, so it is a 0 0 0 0 1 1 1 1 0 0 0 0 1 1 1 1. Okay, I hope you understand this entry. So if I go back to my you can see that y is 0 0 0 0 1 1 1. Only last 4 values are zeros. Okay, first and last 4 values are zeros. So here it is 0 0 0 0 1 1 1 1 1 1 1 1 0 0 0 0. Now you can see that here if you look at this blue oval, there are two quads in this. One is marked in this blue and one is marked in this red oval. Here you can see that the min time corresponding is a bar b. Okay, here it is a b bar. Okay, so it is on o-ring it becomes a XOR b. Y is a XOR b. And now if I look at the last line, that is z, it is coming this way 0 0 1 1 1 3 zeros, etc. This I have to put in a Karnaugh map this way. 0 0 1 1, first 4 are there. Then what is there? Then I have 1 1 0 0. One one 0 0. Okay, so that part is done. Now here it is. Then it is I have 0 1 1 0. Okay, 0 1 1 0. Okay, then I have 1001 last leg 1001. It is a 1001. Okay, now you can see that there are three pairs and three singles in them, so I have to single out these values. So corresponding to this, unfortunately that thing is, the simplification is not there in this. Yeah, here it is here. So why I have computed is that I have to compute. So if you come here, you can see that the one corresponding to this cyan line, that is a cyan oval, that is a it is C complement A complement B, C bar A bar B. You can see the term here, C bar A bar B. Okay, this term is here. Now corresponding to this this violet oval, that is C and A bar B bar. C and A bar B bar. If I come to this this pair, this one and this, okay, what is that? That is CM complement. Okay, CM bar B bar, CM bar B bar, CM bar B bar. Okay, now I have three singles, which is nothing but I must say it is C bar, M bar, A bar, B bar. Okay, C bar, M bar, this is the one, C bar, M bar, AB. Okay, C bar, M bar, AB, C bar, B, M bar. I have to look into this. C bar, B bar, AM. Okay, then there is this one corresponds to C bar, M, AB bar, C bar, M. I think it's a little simplified expression, but from this you can see that it is M bar into this M bar. If I take out, this becomes B XOR C, and here you can see that A bar B, if I take it out, this becomes A bar B XOR C, or AM B XOR C. Okay, quite some steps are there which you have to write. So this becomes this B XOR C I can take out, it becomes M bar or A bar B XOR C, and this is AM B XOR C. So this becomes MA whole complement and B XOR C, or AM B XOR C. Okay, now this AM and AM complement are there, so it becomes AM exclusive or B exclusive or C. So that circuit will look like this. X is the same as A and Y is the same as A XOR B, and here it is A and M, that is XORed with B XOR C, that to get my Z. Now I will demonstrate this operation in Qs. I will close the existing ones. I will open them. Yeah, this is a coder with mode control. I can see that's the same circuit I have realized. Now I run a simulation. You can see that the simulation is running correctly, and you can see that it is performing the computation like this. Like if it is a 0 1 1 with a mode control 1, mode control 0, it's a 1 0 1. With a mode control 1, it's a 100, because one is doing a binary to gray conversion and the second is doing a gray to binary conversion. And here you can see this case, that is a 100 case. Okay, if input is a 111, if it's a 0, mode control is a 0, it is performing a binary to gray, which is a 100. And if it is a gray to binary, if it's a mode is a 1, then if this mode is a 1, here our mode is kept here. If mode is 1 here, it becomes a 101. This becomes a 100. Okay, this is performing the conversion with the mode control. You can try this in Qux. You can follow that design. You can do some simplification. Some simplification steps I think are missing in that. You can go through them. If you have difficulty, please contact me. So what you learned this session, are you designed a 4-bit binary to gray converter using K-maps and tested it. Then you designed a 4-bit gray to binary encoder using K-maps and tested that. Then you designed a 3-bit code converter with mode control and you tested that. And that is the end of this session. I thank you all.